All right. If you if you end up that you can't log in, don't worry about it too much. We're going to go through everything. There's 2 links to the lab document you can always download, and then the deck as well if you want to save this afterwards, and then you can just work through it on your own time. Hopefully, I love the turnout. This is great, but we were only figuring up to 36 folks. So great to have everybody. I'm going to put this up. Kenneth, can you? If I stand here, is that good? Okay, cool. All right, so perfect. We're going to go ahead and get started a little early. We need every minute that we can. My name is Sean Waltman. I work on Geo for Government here at Google, and this is...
I am Mike Lentin. I am project lead for BigQuery JS.
Perfect, thanks, Michael. Okay, so this is going to be interactive back and forth. We were told from the first session that we did this that there is a lot of material. So again, if we get ahead of you, do we have any TAs today? Okay, no. If Shane's going to volunteer, perfect. No, but if we do get ahead of you, don't worry about it too much. Just follow what I'm doing on the screen. Chad did a good job, really good job this morning, hopefully exciting you about BigQuery GIS. And our intention here is to kind of get a little bit hands-on. And I just want to kind of preface that everything that we're showing, if you go back to the first day when Rebecca talked about like walking through glass, there's a lot of that in that particular lesson. And I want to do that so that when you leave here, you're empowered to be able to get your data into BigQuery GIS. But I want to just say that the folks that are really utilizing BigQuery GIS today aren't going to do any of the steps that I'm going to show you. And that's because they're doing it all programmatically. They're streaming geometries and geographies into BigQuery GIS programmatically. And so, this is kind of just coming from I want to use my data, I want to do an analysis, and I currently have it in a shapefile or a CSV file. I'm going to do a brief introduction to GCP and BigQuery, since Chad covered most of it this morning from a high-level view. Talk specifically about BigQuery GIS capabilities, and then we're going to get into demos. We're going to be all hands-on. Once you leave, we'll talk a little bit about how you can use BigQuery in a free tier capacity using the sandbox, and also use the GeoViz tool. Okay, so really quickly, when we work with cloud customers, they say, where should I store my data? And it's a really big question, and we've got a lot of different hexagons up here where you could store data. Different types of applications, and so we sit down and we try to figure out, okay, what does the shape of the data look like? What's the volume of traffic coming to it, et cetera? All of these data stores have the ability to have what I would call basic geospatial capabilities. And what I mean by that is that, for instance, data store, right, which is like our hosted Redis, and memory store is a hosted Redis, basically allows you, it's a NoSQL database, and you can create a point. And then you can write your own Haversine formulas to do a spatial query. But you're writing them, right? What we've added to Cloud SQL and to BigQuery is what I would consider first-class capabilities. Chad talked a little bit about that this morning, about first-class capabilities. And what that means is that you're storing true spatial geographies or geometries, and then you're running actual spatial queries against them. So for Cloud SQL, for instance, a common use pattern is people spinning up MySQL or Postgres, and then with one line installing PostGIS to Postgres. So now you have a managed service that Google takes care of all the scaling and replication and backup, but it's running PostGIS. And so the same thing for BigQuery. Just real quickly between the two of them, like what are the applications? If you're creating ACID transactions, if you're creating a parcel layer and you need to constantly update it, that's a Cloud SQL application. If your application is, I need to click on the screen and do a quick point and polygon calculation, and I don't have Snapchat, number of users, then Cloud SQL is a great solution. Super fast, scaled queries. BigQuery is more of the OLAP type queries. I need to do a gigantic spatial join of all the flights flying over the United States with census tracts, and I need it in pretty quick, but not instant, right? So think about BigQuery as more of like it's a data warehouse, and we've added GIS analytics to it.
So data warehouse is basically a data store where you can drop all your data and quickly analyze it. And what distinguishes BigQuery is it's completely managed. You don't need to think how many machines do I need. You don't provision any machines. You just load your data and you query it. You don't need to update anything or manage anything. And we think it's a great fit for nonprofits, for small organizations, because you don't need IT. You also don't need to think, how much infrastructure do I need to buy? Do I buy five machines and then wait and do coffee breaks, or do I buy 30 machines or 300 machines, and then most of the time they are just spending electricity without doing anything? Instead of that, BigQuery allocates all the infrastructure within milliseconds when you run your query. And that's, we think, is great capability for nonprofits and small organizations.
All right, so here's a little demo of BigQuery. Who here has used BigQuery, just out of curiosity? Okay, a pretty small amount. Okay, so you'll see this is SQL. And what this query is doing is it's going through one of our data sources of Wikipedia, so 100 billion lines of Wikipedia, and it's doing a regex to try to find Goog in the titles, in the articles. And so it's doing 3 wildcard searches here, right? And the data in BigQuery is completely decoupled from the compute. So it's a kind of NoSQL type data store in the sense that we're storing columns of data on disk. And then there's just a constant pipeline of processing that's available. Google uses this to go through all of our logs for all of our products internally, right? And so it needs to be really, really fast, but you'll see that at the very top here, it is ANSI compliant SQL. Now I mentioned the point and polygon example versus really, really large queries. This is fast. It's not Google autocomplete fast, right? It's not sub-millisecond. But still, what we're doing here, you're seeing the result as this query is running. It finishes in about 24 seconds. And to kind of put into perspective about how cool this is, in that time, BigQuery had to go and grab this data set, the Wikipedia 100 billion lines of text, read about a terabyte of data, just raw data, because we compress everything about 4x, and then uncompress it to 4 terabytes. It had to execute 100 billion regexes with 3 wildcards each, and then distribute 1.25 terabytes of data across the network from the storage to where the actual compute happens. To recreate this, if you said, I don't need BigQuery, I can do this myself, you'd need about 330 high-speed SSDs. You'd need about a 330 gigabit network to be able to shuffle all of that data to your compute. And then you need to just have a few, 3,300 cores lying around to uncompress that. So hopefully nobody has that capacity just sitting around. That's why a lot of people come to us to use BigQuery.
So BigQuery JS added vector-based geospatial analytics capability to BigQuery. And it's purely vector-based. If you are doing raster analysis, go to Earth Engine. We are not competing with Earth Engine. We added geography data type and geography functions. If you worked with PostGIS or MySQL Spatial and know all those ST functions, those are the same ST functions from various standard bodies. We don't have complete extension, like long list of functions that PostGIS has, but we have most that's used for typical geospatial analysis. We have basic map visualization capability that you can run a query and immediately see results. And you can import WKT, WKB, and GeoJSON fields. We also provide public geospatial datasets, thanks Sean. And we also do a lot of performance optimizations to make all those queries fast. We do automatic spatial indices. You don't need to create any index like in most databases. We support spatial data clustering. You can cluster if you have like terabytes of data, you can cluster and then queries run faster and cost less. And we support spatial join. One thing that's different from what you might have worked with is you typically work with geometry on a flat map using some particular projection. We implemented geography type instead. It's on a sphere, and the edge between two vertices is the shortest distance on a great circle. And we don't support projections right now, so you need to convert projections to WSG84 before loading. But after loading, you can work on a sphere. You don't need to worry about different projections and so on. And we have a single type that supports all the standard points, lines, polygons, collections of those. And we need that's just infrastructure. What we need is you to do something useful with it. And don't be limited with what you're doing with it, because people are using it even for computing something about stars. Like if you want.
All right, so yes, a lot of astronomy use cases. But let's take it back to something here on Earth. Vermont, perfect time of year to think about Vermont. It's going to be beautiful fall weather starting soon. And the reason I bring up Vermont, as I mentioned, I work with a lot of public agencies. And so talk to Vermont about a problem that they have. There's a lot of effort in a lot of states to get a complete statewide parcel layer. And they're also going through the same time looking at impervious surface changes, trying to calculate rain taxes, stormwater runoff. And so these are a work in progress, these layers. Obviously, the impervious surface layer is changing forever. And the parcels, sometimes it's a little bit of like, hey, we got to go to this county or this town and get them to share it with us. So what we're going to show you today is a little bit incomplete. But currently, there's 204,000 statewide parcels. And so a query that very commonly has to be answered by the state GIS is, okay, how many of them have impervious surfaces, right? This is a query that you could imagine them having to answer. So let's take a look at this and break this down. These are some of the layers that we'll be working with today. On the left-hand side here, you see the incomplete parcels for Vermont. A couple townships are missing. We have a very nice, from a 3DEP grant LiDAR collection, we have an impervious surface that includes roads and buildings, et cetera, as impervious surfaces. And the question that they were just trying to answer was, just tell me how many of the parcels have impervious surfaces on them, and what does that intersection look like? So when you do this today, they're probably going to do it in ArcGIS or QGIS or maybe in PostGIS. So let's take a look at PostGIS. What we'll do is write a SQL query that says, give me the count of the distinct number of parcels that have an intersection with the impervious layer. This was done on a pretty nice workstation, my Google workstation. So it's 12 core, 12 CPU Core i5, 32 gigabytes of RAM, and I had to build a spatial index to do this, and it took me 39 minutes to run that query. Okay, so now I got the answer. 192,000 of the parcels have impervious surfaces, but it took me a really long time to do that. So what we're going to do is see what writing that query looks like in BigQuery GIS. Okay, so to do that, we'll follow along in our quick lab. We've got our environment set up, and you scroll down here to the intro to BigQuery GIS spatial queries. There's going to be a query. All right. The nice thing about Quick Labs is it automatically builds this little copy button for you, so you can just click that copy button. And in your Google Cloud Console project now, yeah.
Is there anybody who's stuck on getting the environment set up that would like some help?
Nope. Okay, cool. If there's any problems, we've got TAs, Don's here, Shane's in the back, Chad's here.
One more.
And we have one more login if somebody wants to log in. All right. In the Google Cloud Console, you may be familiar with this if you've been starting to export stuff from Earth Engine. There's a lot of different products. What we want to do is scroll down to Big Data, and you'll see BigQuery. A neat trick is that you can click this pin icon, and now for this project, for me, BigQuery is going to be pinned to the top. So I'll go ahead and click BigQuery, and it's going to give me, because it's the first time using it in this project, it's going to say, welcome to the Cloud Console and the new UI. All we want to do is paste in that command that we copied into BigQuery and then click Run. So remember, this took 39 minutes to run on a really nice PostGIS installation. What you're accessing now, you can see this vtsolar.vt data. These are data sets that I've created in another Google Cloud project, and I've made them publicly accessible so that anybody can query them. And what they are is, one is the parcels layer and one is the impervious surface layer. So right now you're running the query in your project, but you're querying against my data. Okay, so it took 22 seconds. It processed a gigabyte of data, and it took 22 seconds. Did I mention that? Right, so not 39 minutes. So the coffee breaks in Vermont are over. Okay, so yeah. Okay, so that was a pretty cool query. So let's now make it an order of magnitude harder. So okay, we have 204,000 statewide parcels, and we know 192,000 of them have an intersection with an impervious surface. What percentage of the parcels are actually impervious? So take a look at this. Very nice home here somewhere in Vermont. And we see that there's a parcel layer that includes the driveway and the actual like surround of this house and that nice tree. So what we're asking is, we're going to bring in the impervious layer, and we want to calculate the percentage of each parcel that's impervious. Okay, so this is something that if you were considering a statewide or a countywide rain tax for runoff, and you want it to be equitable, you want to calculate this and encourage people to do things like putting green roofs. And so this is another very common query that you would be asked. So I didn't get a screenshot of trying to do this locally, but it's probably something like this. Right, and that's the reality, is that we heard that what they do is when these types of queries come in, kick it off at 3:30 in the afternoon, and then go do something else, go home for the day, and in the morning, hopefully ArcGIS didn't crash, or PostGIS didn't crash, or timeout. And so that's kind of the reality when you're trying to do this, and Vermont is not our largest state, but when you're trying to do it at a statewide level, that's the reality of today. All right, so we're going to go back to our quick labs. We're going to now run this next query, which is going to be that larger query. So this is under section 2, the more advanced spatial query, and you can see that it's a larger query. In this case, we only do support inner joins, but we're going to emulate an outer join with a custom selection here. Yeah, you want to talk about that?
We only support geospatial
and
inner
geospatial
joins.
Yeah.
You can run outer join, but they will not be geospatially optimized.
Yep. Thank you. It's great to have Michael here to correct me, so I'm not telling you the wrong thing. So okay, so we're going to paste that in there. It's a larger query, so we expect this to take longer to run, and it will. Let me see if I can just pop this up in size a little bit. So what we're doing is, for every place where there actually is a parcel data, we're going to calculate its impervious area percentage and divide that by the total area of the parcel itself. And then we're going to round it and multiply it by 100 just to make it nice and human readable. And then basically we're going to join that. We're going to use, this is the outer join piece where I'm actually creating the function to do parcel impervious area to join that. And then I'm going to order this by the parcels that have the highest amount of impervious percentages. Okay, so this one is chugging along. It should take somewhere in the order of like 90 seconds to run though.
So while we're waiting, is there anybody that needs some help to get the console running?
We're good? Great. All right. So that took 71 seconds to run. And so I just did that really complicated equation for the entire state of Vermont and our entire data set. And now, who's got a sharp eye here? I sorted this so that we could find like the most impervious percentages, and what should the largest number be if that's the case? 100. And our answer is 200. So either I'm really bad at my SQL statement, or there's something wrong with this data, or both. Okay, so how do we investigate this? Well, we've got an object ID, so we have a unique ID for the particular parcel, and we know the town is in Essex. So what we're going to do, if you go back to the quick lab, is we're going to use a tool that Don actually built here, Don McCurdy, called the BigQuery GeoViz tool. So just click on this link, and it'll open up the BigQuery GeoViz tool. This is the tool that allows you to run a BigQuery query and see the actual geometry. So Don takes care of grabbing the data and generating it as a GeoJSON and drawing it to Google Maps. Now, this is a tool that has no idea who you are. Okay, it's completely agnostic. So what we need to do is grant this tool permission to access your project and your data on your behalf. So to do that, we're going to do the OAuth dance, as we call it. We're going to click on the Authorize button, and it's going to say, okay, who are you? And so we're just going to click on the student account that we're signed in with. And now it's going to come back and ask us, do you want to grant Don's application the ability to access your Google account? And this is always, whenever you see these, take a look at what they're asking. right? This is basically saying I want to manage your data in BigQuery. And Google's telling you to use this tool. It's open source and we're standing behind it. But if this says, and we also want to be able to send email on your behalf, like be suspicious about what you grant access to, right? Because opening up your Google account. So click allow, and then we have to pick our project. So this is going to use the BigQuery API to run a BigQuery query in your project. It's just doing it in a third-party application. So click on project, and there could be some other projects that are associated with this account. Go ahead and pick the one that's Quick Labs GCP something. Okay, now we're authorized. We're going to be able to run a query against our project. In the code lab, there is, after you get through all of this, there's a query I want you to run down here, right underneath where we talk about the 200%. Click on the copy button, and rather than running the query in BigQuery, we're going to run it in the query editor that Don's built for us right here in GeoViz. Okay, so what it's saying is I want to run an intersection and return the geometry of the impervious layers where they intersect that particular parcel by using its object ID. Okay, so this will take a couple seconds, and you see a big red circle. And help to try to understand this, go ahead and click on the satellite button, although that will tilt us since we just flew this area in 3D. It'll tilt us to this. We correct for that by, on the right-hand side here, we have a tilt map button, which will change us back to our ortho view, where the geometries can be overlaid. Okay, so now we kind of understand what's happening here. Basically, this is a really fancy Vermont cul-de-sac, and basically, as I hover over here, you see the two layers changing. The parcel is actually the middle of the cul-de-sac, and it's completely covered by one impervious polygon and a second impervious polygon for the road. So it is actually 200% covered. So this is just kind of pointing out that when you do these large queries, it's a good way also to be able to find potential defects in your data. So it's a good idea to be able to check that and do it quickly. So we could stylize this, but we're going to just move along here. But you should be able to see as you hover over it that they are, in fact, two distinct geometries. Okay. Right. So what if I wanted to say, okay, what if I now want to take that result and I want to find all of the towns and aggregate by the town. So take all the parcels that we know their percentages, and we want to now aggregate by the town, because I have a hypothesis that more urban areas will have larger percentages of impervious surface cover per parcel, right? Think about small urban lots compared to a large, dairy farm in Vermont. There's going to be a larger percentage, I would imagine, of impervious surfaces on the urban lot. Okay, so in the BigQuery UI, copy this command, and we're going to run this new query in BigQuery GIS. I'm sorry, in BigQuery, to get our list of towns. So we're taking that same query, but now we're going to do an additional group at the end to group by the town and then order by the average percentage. And this should give us a list of the towns that have the highest average percentage of impervious surface coverage per parcel within that town. All right, everybody kind of on the same page? We're moving along here. Any questions while we're going through this? Yeah?
What language is this?
So the question is, what language is this written in? This is SQL. So this is ANSI compliant SQL, which is kind of the really cool thing about BigQuery is the fact that it's storing data in a column format like a, yes, Chad?
Oh, sorry.
Oh.
Next question.
Okay, it's storing data kind of like you would store in a NoSQL database, but you're actually able to write ANSI compliant SQL and use, in this case, the same type of spatial predicates that you do and functions that you do in PostGIS. Yes, Chad?
How many people in the room are already familiar with SQL?
The question was how many people in the room are familiar with SQL, and I would say it's about 85–90%.
Right, those not, feel free to pull the TAs over.
Yep. All right, so we got a result here that shows us that descendingly, we've got Winooski, which is right next to Burlington, and then some of our bigger ski areas, Rutland, Stratton. So Montpelier as a capital, kind of what I was expecting. But I'm a geo person, and I really want to be able to look at this as a map. Okay, this is where there's a lot of steps, so we want to make sure that everyone's kind of tracking along. what we want to do is first, we're going to go into BigQuery and we're going to create a data set. Because what we were going to do is we're going to go grab a shapefile and we're going to bring it into BigQuery. We're going to grab a shapefile of the town boundaries so that we can take those results and then actually map them. So in BigQuery, what we want to do is copy this G4G underscore dataset. And over here on the left-hand side, you see your project name. If you click on that, now you can click on the button that says Create Dataset. And it's going to ask you what you want to call it. We want to call it G4G Dataset. Data location, for this purpose, it doesn't matter. If you're working in the EU and you have a reason that you need to be able to store it in Europe, we give you the ability to choose where your data is stored. Okay, so table expiration. There was a question in the last session, well, how long does this stay there? By default, after 90 days, we will cycle it down to a lower cost storage. But you can also say that this is temporary, it's going to be a BigQuery, but I don't want to pay for it the entire month. Let it live for 2 or 3 days and then delete itself. You can also change the encryption. If you don't trust that Google security is going to protect this data, you can actually store it with your own managed key. So if you have that requirement, Google literally can't see what the data is that we're processing on your behalf. But just go ahead and click Create Dataset. And now you'll see on the left-hand side here that we have, if you click on this little triangle, we now have an empty dataset. Datasets can be shared. If you look at the VT Solar, that was my VT Solar project. The VT data was a dataset that I created. These dataset names are unique per project, which is different than Google Cloud Storage Bucket, which are globally unique. So everybody can have the same G4G underscore dataset. Okay? All right. So now what we're going to do is, I find the best way to do this is to just copy the URL from the BigQuery environment and then paste it to another tab. So we now have 2 sessions going on inside of Google Cloud Storage, in the Google Cloud Platform. And we're going to go and create a Google Cloud Storage bucket. So who's created a bucket before? Who's exported stuff from Earth Engine and created a bucket? Okay, so this should be pretty straightforward. We want to come down here under Storage and Storage, and pin that. And this is going to, when we click on Storage, this is going to take us to Google Cloud Storage buckets. Now, I just said, when you create a Google Cloud Storage bucket, it is globally unique. So test bucket 1, these are all gone. Okay. Okay, so
Test bucket 1, test bucket 2, they're all mine.
so for this lab, and this is where the copy and pasting gets a little tricky, is because you actually have to remember what you call your bucket. So I'm going to click on this. I'm going to call mine G4G 2019 Wednesday.
Beat him to it quick.
Yes. And just click all the way through. I got it. All right. So call it something like that. Just something that you're going to remember. But when we copy and paste later, from when we actually interact with this bucket, just remember you're going to have to remember what you call it. Okay. Everybody doing that? I'll give you a couple seconds.
I claim G for Good 29 Wednesday 1.
Perfect. Perfect. Okay, so that's cloud storage, and this is our object storage. This is where if you need to upload, billions of video files, or if you're uploading hundreds of millions of tiles that you're exporting from Earth Engine, this is our object storage. There's one global endpoint for it. You can set all the different storage classes on it. There's a ton we could talk about, but just know that this is where we're using object storage. The reason that we're doing this is that when we use some of our tools, they don't want to work with your local file system. They want to work with like a globally accessible cloud-based file storage. So like when we load data to BigQuery, it wants that data to already be somewhere in the cloud so that it could spin up a bunch of machines to go and ingest it and harvest it. Okay, now do the same thing again. We're going to copy this URL and open up a third tab, because now we're actually going to go and create a virtual machine. So to create the virtual machine, click on the menu. Under Compute, we're going to go to Compute Engine and VM Instances. Okay, who's created a virtual machine in Google Compute Engine before? Okay, all right, about 5% of the class, 10% maybe. Okay, so these are containerized VMs. And basically, Google manages the base images. You can bring in custom images. If you have a Windows server, you can actually bring in your own license. But we provide a scanned version of the most common distributions, mostly Linux distributions. So we're going to go ahead and click Create. And I really need you to pay attention on this one. Don't just click through it because I want to go over a couple of different things. First of all, the default is fine. This machine's not going to do much. It's just going to download a zip file, unzip it, convert it, and upload it. But we have the ability here that if you needed to run some monster of a machine, you can have like maximum number of like 256 CPUs and whatever it is. It's crazy. But just also remember that these are always containerized. One of the really cool things about Compute Engine is during events like Spectre and Meltdown, 100% of the VMs that were running in Google Cloud were migrated with zero downtime. So they got moved literally to systems where those vulnerabilities were patched, and we did it with zero downtimes. Users never even realized that the machines had been migrated. All right, we're going to go with the stock Debian stretch image here, which is the default. Now, this is the really important piece. Click in the access scopes. Allow full access to all cloud APIs. This is not a best practice. However, what this is going to do is when we actually create this virtual machine, it's going to have the scope to work with all the rest of Google Cloud Platform. So we're granting this VM a lot of privileges to be able to say write to a Google Cloud storage bucket. What we typically do is give you default access, and then the operator of the virtual machine would log in and authorize with their own credentials, but we're not going to do that today. Okay, so that's the most important thing. Now we're just going to hit Create. So this is going to spin up a 1 CPU machine that's going to be called Instance 1. And it'll take a couple seconds to actually be available. And when it spins up, it will have a external IP address. And that external IP address, in this case, 34.69.164.62, is ephemeral. So if I stop this machine and turn it back on, I might get it again or not. If you need this to be a persistent VM, you can make that a static IP address. So what we're going to do, though, is we're going to use a cloud-based SSH terminal. So all you need to do is click on SSH, and you're going to open up this little window to connect into your virtual machine. And so what it's doing right now is it's taking your browser credentials and it's passing those as SSH credentials, logging you whatever your generated student username is as a user to the VM. Okay, does anybody need help?
Quick question, can you set up a VNC server?
The question is, can you set up a VNC server? Yes, you can. You have to enable, by default, the firewalls will be set up so that a lot of those ports are blocked, especially if it's Windows. They just had a big issue. We've patched it, but the RDP issue that they had with Windows. A great thing to do is if you do install a Ubuntu or Debian image and you want to use a remote desktop, is to use the Chrome remote desktop. And then you can just basically connect to this using the remote desktop extension for Chrome, and you get the full desktop experience. Yep. Okay. All right, so now we have a VM. And like I said, what we want to do is we want to go, the whole reason we're doing this is to go grab a shapefile and then do something with it to get into BigQuery GIS. Okay, so if you scroll down here past all of this, the first thing that we need to do is to update the operating system's packages list to the latest versions. So there should be a command here that says sudo apt-get update. So go ahead and copy and paste that. Yep, no problem. So that went ahead and got us the most recent versions of the packages. The next thing that we want to do is get the actual tools that we're going to need. Who here knows what GDAL is? Okay, yeah, Swiss Army knife of the geo world. GDAL has a utility called Ogre, OGR to OGR, which we're going to use to process our shapefile. So go ahead and click this copy command, and then we're going to install both GDAL and unzip, because we're going to get a zip file, essentially, that we need to inflate. Okay. The nice thing about the GDAL bin package is that, this used to take potentially hours for you to go and build all these different libraries. People, I think you see Tao laughing because he's probably done it about 7 million times in his life. And so like the nice having that GDAL bin package, now I actually have a GIS machine running in the cloud in a couple of seconds. And just to double check that, what you can do is just type in which OGR to OGR. And now I know that this tool that we're going to use is installed. Okay, so now we want to grab those town boundaries. And they are currently hosted. This is a layer that Vermont CGI hosts. We don't want to send a ton of traffic to their website unexpectedly, so I've copied this and put it into my own cloud storage bucket. But we're basically going to grab this zip file and click on this little copy-paste button here, and we're going to use wget. Oh, I'm sorry, no, we're not. We're going to use gsutil to get this. gsutil is part of the Google Cloud SDK. It's a utility that allows you to interact between. Oops, sorry. It's a utility that allows you to. Yes, I made that GIF, the meme earlier. It allows you to interact with cloud and local storage. So this command is just saying use the gsutil utility. I want to run the copy command to take the file that's sitting in GS or Google Cloud Storage, VT prep data, and then it's a zip file, and then make sure you have that trailing period that says I want to download it right here to my home directory. Okay. All right, really small file, should only take a couple seconds. Now the next thing that we want to do is unzip this. So we're just going to hit unzip. All right, there's a command here to do that. Just unzip Vermont data town boundaries. And you'll see that, like many shapefiles, they're packaged along with all of their sidecar files, right? If you were going to upload this to Earth Engine, you would just upload that zip file and it would have all the sidecars alongside of it. Okay, now I want to understand what this shapefile is. So the way to do that, there's another nice utility from GDAL called OGR info. And OGR info, I'm going to use the AL to go through all of the information about the shapefile, but then I also want to do SO, which will give me a summary. So I want to do OGR info AL SO, and then I'm going to use the shapefile. All I need to point to is the shapefile itself. So now Ogre gives me a really nice summary about what this data is, and we'll walk through a couple of important pieces. The first part is the layer name. So shapefile has this ability, similar to a file geodatabase, to have a layer name. In this case, it's the same name, and in many cases, it's the same name as the shapefile itself. So we know the layer name is VT data __ town boundaries. We know it's polygon. There's 255 features in this particular shapefile. There's its spatial extent, and then there's some projection stuff. Is this going to work in BigQuery GIS? Why not? That's right, because it's projected. This is in Vermont's, it looks like UTM, some sort of Vermont, yep, 1983. So we need to do something about that. And at the bottom, it'll also show me all of the fields. And this is going to be important because we have to be explicit about the field types that we put into BigQuery. BigQuery does have the ability to auto-detect, but you'll find, especially when you start to work with really, really large data sets, that it'll only scan the first maybe 100,000 rows or so, and darned it if the 100,001st row is going to be the wrong data type, and it'll fail on ingest, right? So we want to be explicit, which means that we want to actually describe our schema. So this is going to be information that we really need to know. Okay, so scroll on down here. There's a command that we're going to copy and paste for OGR to OGR. That's the actual piece that's going to take our shapefile and turn it into what we need to upload to BigQuery. And what we need to upload to BigQuery is going to be a CSV file. But it's going to be a special CSV file. Okay, so let's walk through what this command is doing before we run it. So it's OGR to OGR. -F means the output is going to be a file of a CSV type. And then we're going to use a dialect. The dialect piece is going to allow us to specialize SQLite, which is one of the supported dialects of OGR to OGR, specifically SQL. And the reason that we need to do this, let me see if I can blow it up any larger, is we're going to use a predicate or function for as GeoJSON. So for each row, we're going to take the geometry from the shapefile and turn it into a GeoJSON. But before we do that, we're also going to transform it. So we're going to transform it from whatever projection that is in Vermont, well, we're going to unproject it to EPSG 4326, which is what BigQuery needs. And then we're going to call that field the geom, and then we're going to take the rest of the fields. The VT data underscore town boundaries, that's that layer name, right? Now we want to use the output, and we want to call it VT town boundaries.csv, and the input is the shapefile. Okay? So we do that, and a couple seconds, not a huge shapefile here. And if we want to take a look at what the headers look like for this, we could just do head-1 VT town boundaries.csv. And you can see now these are the header fields for our CSV file. We've got the geom, the object ID, the FIPS code, which is a state, federal code, town name, city, et cetera, et cetera. Okay, and we know each one of these, what they are, whether they're integers or strings or what have you. If you really want to do this to understand what this looks like, you can also just take the second line as well, but it's going to fill my entire screen because it's going to actually print out, that's that GeoJSON of that first row, that first town's geometry. Okay, so it's a CSV file, but one of the fields is a spatial field. And by the way, you can open this up in QGIS if you wanted to, and QGIS will detect that and then draw it on the map, even as a CSV file. Yep, we have a quick question.
The 4326 report in the transform, that was the target.
Yeah, that's correct. So the question was the 4326 the target projection? Yeah, so we're saying to transform it to 4326. That's the desired SRID. Okay. So we did this. Now we have the CSV file locally. In the documentation here, you'll see we go through and say, okay, this is an integer, a string. That means that when we go to load this, we're going to have this schema that talks about a key, which is the field. So the geom is going to be a type geography. The rest of them are going to be whatever they need to be, integers, strings, etc. Now we need to get this file off of our local file system and into Google Cloud Storage. So we're going to use gsutil again, but remember, you can't just copy and paste this because you had to create a unique bucket name. So gsutil copy, vtboundaries.csv, and g4g, what did I call it? See, I forgot. Yeah, 2019 Wednesday, thank you. So whatever you called your bucket, you need to change this command. And what this is saying is simply copy CSV to that bucket. All right, who got stuck there? Or are we good? We're good? Great. So if I look in my Google Cloud Storage bucket, I should see a CSV file that's been uploaded, right? So I just use that gsutil command and it's uploaded now. Okay, another utility that comes in the Cloud SDK is called BQ. What does that stand for? BigQuery, good job. And so we're going to use, yes, we're going to use the load function. And this command is basically saying, I'm going to load with the source format of CSV, because it could also be, you could actually create a new line delimited JSON file. So I'm going to use CSV. I'm going to skip the leading rows because we don't want to ingest the header. So this tells it that there's a header. -- for place, that says that if this table currently exists, overwrite it. This is very common in BigQuery. You cannot update a BigQuery table. You can make a new version of it. And the next piece is the actual schema. So that's the line where we generated from OGR info. And then it's going to say, we want to put this in our G4G data set, which we created in BigQuery. We want to call the table VT town boundaries. And then we need to change this code to match your bucket name. So we're telling this tool to create a BigQuery ingest job on your behalf, right? So we're going to change unique bucket name to G4G 2019 Wednesday, in my case. You could do this too, actually. No, you can't. It's not shared. If I had shared it, you could do that. And we're going to go ahead now and load that into BigQuery. And it is a very small shapefile. It is being read by multiple machines from BigQuery, so we do not expect this to take a long time. In 4 seconds, now that CSV file has been ingested into BigQuery. Yep.
So if you can't update data sets, let's say you have streaming data, that's why you need the
Right. So yeah, we'll talk exact. So the question was about like.
You, yeah. Oh,
Go ahead, okay.
repeat. So the question is about you cannot update the. So you can insert into a table.
Okay.
You can add data. You can update. You can update existing table using update command, but we are really not optimized for that. So you can only issue a limited amount of update commands per day, and uh, the performance would not be like a single update would not be as efficient as updating it in OTP database.
Okay, so now everybody, if you go into your BigQuery data set, you may need to refresh it. The UI doesn't automatically do that when you ingest a table. So you might need to just refresh that. But now under your data set, you should see VT town boundaries. And if you click on it, you see here's the schema that we defined, geography, integer, integer, string. The details of this, I should see 255 rows. And then for a preview, I can click on this and I can see the geometry field, which is really large because it's a bunch of GeoJSON for a town, and then the object ID and all those additional fields. That was painful. That was glass crawling, right? But the point of this is, like I said, most of the folks that are using this at scale aren't doing this. They're just ingesting, they're writing their Python code to just create a geometry from some connection and streaming it into BigQuery. But I wanted to make sure that you were equipped to do what was probably going to be very common, which is to take your data, which is probably in a shapefile or a database, and get it into BigQuery. Okay, so now we have a table that has that spatial extent for the towns. So what we're going to do now is we're going to go and copy a similar version of our previous query, except now I'm going to do an additional join that's going to do a left join to take those resulting tables and marry them to the geometries of the town that we just created. But don't run this query yet. The reason we don't want to run this yet is so far when we've been running queries and getting this output on the screen, that's the only place that the output is gone. And if we close the browser tab, that data is lost. So these can be expensive, not really expensive at this scale, but they do take up your compute time and they take up the storage time if you do store it. So we want to make sure that if we're running a big command, that we're storing this as a permanent table. So the way that we're going to do that is we want to call this eventually impervious percent by town. And we're going to go to the query settings. So we've pasted our command into BigQuery's editor. We're going to go to More, Query Settings. And like I said, so far everything has been to a temporary table. And you've just been able to preview it and page through it if it was really large. What we want to do is set a destination table. We want it to be in our project, and we want it to be in our data set. But notice this, you could actually be writing to somebody else's project. So you can work collaboratively and say, I want to run a query in my project. If you've given me permission as an editor, I can dump data into your project. This one we're just going to dump into our own project. The table name is going to be impervious percent by town. And then we always want to click this allow large results. By default, just to make sure that you don't accidentally run something gigantic, BigQuery has a quota set on it. If you click on this box, which we don't need for this table, but I just wanted to show you that you should always do it if you do expect it to be large data, is to allow large results. Then we have these options, write if empty. This could save you from accidentally writing to a table by accident. And then append to table, which is add it to an additional table, or completely overwrite, create a new version of that table. So we're going to keep all the defaults there. Destination table for the results, click save, and click run. And this again will take about a minute or so because it's going to do that large intersection query for all the parcels, and then it's going to join it to the geometries based on the town name. All right, while this is running, any questions? Yes?
Can you specify these options in the code itself without going through?
Yes, yes. So yeah, Michael, if you want to elaborate on that.
Yeah. So another way to write to a table is to do create table as select, and you don't need those options. So that's just another way to do it.
So you can do it. So the question was, can you do this without going through all the UI pieces? And Michael said yes, you could do create table as select like you would do in PostGIS, but you can also do it from the command line. So or you could do it from one of the client libraries. So you can do it from Python, Java, Go. I'm missing one probably. So yeah, so you don't have to do this necessarily from the UI.
Can you specify basically the table name and project callback?
That's right. So you specify where you want it to go in the, whether either it's in a library or in the command line. Okay, so now everyone should have a new table that's called impervious percent by town. And if you see the results here, you see a geometry field and the town name and the percentages. Okay. At this point, you have a design decision. How many people have QGIS on their desktop or on their laptop? Okay. For those of you that have QGIS, go through the lab and export it to a CSV file, and you can visualize it in QGIS if you want. Or we could look at this in BigQuery GeoViz as well. The lab will let you choose either one, or do both. The nice thing about QGIS, as I mentioned, is all you need to do in either 2 or 3 is add this as a delimited text layer. When it comes into QGIS, you go ahead and it'll automatically detect a field. It'll detect the geom field and know that that's well-known text. However, what you will have to do, because it's a CSV file, one second, Chad, it is a CSV file, you have to tell it what projection or not projection it's in, and tell it that it's 4326 because the CSV file doesn't have that information in it. And the result of that is now you can use all the nice, natural breaks and all the nice classifiers inside of QGIS. If you're doing it in QGIS, that's great. For everybody else, we're going to build our Chloroplast in Don's tool in BigQuery GeoViz. And to do this, I'm going to clear out this code. I gave you a little snippet that just says select star from our data set and from our impervious percent by town. And by default, that's the nice thing about saving that table is now I didn't have to wait to go and do that whole spatial join again. It's already built. I already have the data stored. So now I've got a very red map of Vermont. And so I want to look at the data. If I click on data, I see, okay, town name, average percent, and the geometry. If I go down to add styles, I want to use a data-driven approach to do these styles. So to do that, I'm going to look at fill color, and this is going to click on to data-driven. What type of function do we want to use? This is going to be a linear function. I probably want to have 2 or 3 domains, and I need to select my field to tell it which field has the data that I want to build my Chloroplast map by. So average percentage in this case. You'll see that Don automatically for me gives me the min and max. So I'm going to put 0 in this first box. I'm going to put 24 in this middle box, and then I'm going to put 43 in this top box. And now I need to pick my colors. So since this is going from low to high, I always think about that as green to red. I'm going to go green, yellow, red. And pretty quickly now, the GIS person in me is satisfied. I can look at the whole state of Vermont, and I can realize where we have my theory that said that the more urban areas are going to be the ones that have the highest percentage of parcel coverage that is impervious. Any questions? Okay.
Did you set the opacity or it's
By default, I guess it has some sort of opacity set there. You can change that opacity, so I could drive this to 80%, or if I really wanted it light, to oops, I did it the wrong way. So you can adjust that. You can also change the lab has you change some of the colors as well, for the outlines. Now, currently I have this set to 0, but if I set this to 1, no, never mind, that didn't work. Anyway, and the nice thing about Don's tool is also you can always click on these individual GeoJSONs to get the data. So I know that this Burlington is 42% on average. Okay. All right. So everything that we did so far has been, cut and paste, and everything has worked great, right? And you're going to leave here, and you're going to go grab your shapefile, and you're going to go and import it, and it's going to fail. The reason for that is that, it may not. You might luck out. That one worked. But the reason for that is that, as Michael mentioned, the support in BigQuery GIS assumes all geometries are valid. Who here has worked with bad geometry? Everybody. Okay. Yes. So basically, what this means is, and if you take a look, this actually comes from our friends at ESRI. But there's lots of different ways that your shapefile and vector data can be messed up, especially if it's something like an impervious surface layer, which is auto-generated, right? So what can happen is that you've probably done this if you've been digitizing and then you accidentally cross your polygon. GIS packages like QGIS, ArcGIS, they'll typically open up, and so they'll actually show you the shapefile. But as soon as you try to do something like a spatial analytics against them, it's going to do one of two things. It's either going to fail for the entire layer, or it's going to exclude the layers that are broken. There's lots of ways that you can mess up geometry. Okay, so to show this, we're going to go back into the code lab here, and we're going to run a BQ load job from an existing data set that I've shared. In this case, I took that impervious shape file from Vermont. I just put the raw conversion from OGR to OGR and just created a CSV file. So this is a really large shapefile. We're not going to actually import it in this class. All we're going to do is copy that BQ load command and run it. And when it goes and creates the job, it's going to get a couple rows in and say, hey, we've got a problem here. There is something wrong, and I am canceling this job. And it shows you that right away there was an error processing the job because there's too many errors. And if you look at it, it says could not parse the type. Edge 6 has a duplicate vertex with edge 9. Okay, two ways to solve this right off the bat. First thing that you can do is there is a tolerance that you can change in the BQ load command, and you could set the max bad records equals X. You can put that at 1,000,000, and it'll say, okay, I'll just encounter these errors, but it's going to drop those. Okay, so basically, don't do that, because if you're trying to have a complete data set, it's going to drop those rows. But if you wanted to just get a quick and dirty import and see how many bad records you have, you can certainly do that. Another way that we can do this to investigate is, rather than ingesting it as a geography type, we can just ingest this into BigQuery GIS as a string, right? Because it's just a string after all. It's not actually a geography yet. When we tell it's geography, it's behind the scenes, it's running the stgeog from text. So if we do the same thing, I've ingested this already. We're not going to go through again because it's so large, but this query is going to go query the string version of that table, and it's going to use something called safe. So I clicked run, and I got a warning to say that, hey, your impervious town is going to be overwritten. I don't want that to happen. So just go to query settings here and disable storing this. We're just going to save it as a temporary table. So while this is running, Michael, do you want to talk a little bit about safe? If I can find the slide.
Hey, for those of you that had trouble finding the data set, I've added to our public data set program. So if you look over the board at the bottom, you can see my handwriting got progressively smaller as I wrote, which is something I'm not realizing for the first time. But you can find the same data set that Sean was working with there. So if you fell behind throughout the lab, you can still catch back up and do some of the analysis there.
Perfect. Thank you, Shane.
Safe is a prefix that you can add to many functions, especially functions that import some data and that are expected to fail on some bad data. So instead of writing stgeog from text or stgeog from GeoJSON, you write a safe dot and the name of the functions. And safe version of the function doesn't fail. It just returns null. It doesn't magically import that data, but it allows the whole import to work, and the row will be ingested, the geography value will be null, but you can analyze the original row value and fix it up in some ways that we'll talk about.
Yep. Perfect. So yeah, so the query that we just ran before we came back to that used that safe, right? So if I look at this query here, I did basically the query that I ran, which is still running, says select all the fields from the impervious text import, and any place where the geometry is not null and the safe inspection is not null. So what this is basically doing, as Michael said, is it's going to return null if it's not a valid geometry. So this is large. Again, it's taking up this gigantic, couple gigabyte CSV file, and it's checking every single geometry as it's ingesting it and trying to convert it into a geography.
Is null or is not null for the very last one?
Is null.
So it's rows where geometry is not null, but when we try to import it into BigQuery, we get null. So it's something that was not valid from the BigQuery point of view.
Correct. Problematic ones, exactly. So what this returns is basically a list of the 1,271 invalid geometries for that particular layer. Okay. However, you'll notice that we did use a fixed version of that in our queries, right? I got to the point where we actually have the complete geometry set where I fixed those 1,271 errors. There's two ways to do this, and one of them works. So to do this, what we can do is in the step back where we actually use OGR to OGR, is we can add, because it's SQL, we can add this stMakeValid. So before we transform it, there are tools in SQLite that allow you to actually make a geometry valid. It may not work all the time, but they're pretty good. The problem, and the reason that we can't demo this, is that this recently changed. Remember how I said it was really nice to be able to just install gdal bin and get all these nice geo tools? All of the binary packages that are made for Debian and Ubuntu right now do not have this particular function built into the Spatialite dialect. And that's because under the hood, there was a change from using libwgeom to rtopo just recently, and none of the packages have caught up to that. So if you're somebody who is really good with building gdal from scratch, there's not also instructions anywhere in terms of how to actually get this built. But supposedly it does exist. So when eventually this comes around, this will be nice because right there in your virtual machine or on your desktop, you'll be able to make valid all those geometries and then be able to upload it all in one step. So how did I actually fix this? The second way does work. It just has a lot of overhead associated with it. But it turns out that that's not such a big problem. What I have here is kind of a diagram in terms of how realistically BigQuery GIS is used in the field. Like I mentioned the parcel example. They might get a new parcel comes in from a town that they didn't previously have. Or a GIS analyst goes out and digitizes a new parcel. They're going to be doing that transactionally, right? They're doing that either locally, or maybe they're using Cloud SQL or PostGIS on their own network. And so they're using a database behind the scenes. As we've shown, like you want to be able to do these large queries. That database may not be the place to do them. So you want to get that data over to BigQuery. There's two really cool features of BigQuery that allow you to automate this. The first one is federation. You can actually, in BigQuery, rather than downloading and importing, you can now connect to Cloud SQL, you can connect to Sheets, a couple other places you can connect to, other Google databases, and write a SQL query that says, import from my PostGIS database. And the next piece that's really cool is scheduled queries. So you might imagine that I have a transactional database where I'm editing the parcels all day long. Every night after work, I want that query to automatically run and update the table that I have in BigQuery. And you just set that up, and then it'll just run until you turn it off. Now, two things you can do, either as a scheduled task in PostGIS or during the query itself, you could actually just do that make valid command in PostGIS, either in the transport or locally, and so they were always bringing over a cleaned version. So to get the full VT impervious layer, I ingested it into PostGIS and then exported a CSV file using the stMakeValid, and so I fixed those 1,271 features that way. And the nice thing about that is, you know, if I'm Vermont, now I have my data warehouse, I can answer those questions quickly, and then I can also explore the data. What we're starting to find, especially when you get to these large data warehouse scales, you don't always need a map. It's nice to have a map, but if you're doing a time series of impervious surface change per county over time or something like that, that's just a time series. And there's great tools. There's a free tool called Data Studio, which will allow you to do that. Or if you're familiar with Tableau or Looker, which Google just purchased, you can use those to build those types of dashboards. Okay, the next piece, not to put you on the spot, Shane, do you want to talk about this at all? Or okay.
Yeah, I'm using the mic as a
Yeah.
show we're recording here.
Okay, hey everyone. My name is Shane Glass. I am the program manager for Google Cloud's Public Datasets program. So if any of you have used public dataset in Google Cloud Storage or in BigQuery, that's the program I manage. So we onboard, update, maintain, whatever else, a litany of datasets. We have 140 some odd datasets, probably closer to 150 now at this point. I won't go too far in depth because I'll make a very subtle plug for my session this afternoon that you should all attend because it's going to be great. Where we'll kind of walk through where you can discover public data sets and some use cases and how you can utilize them. But in the meantime, if you're for whatever reason otherwise occupied, like, I don't know, you're getting married or something, it's the only logical explanation I can come up with, then I encourage you to check out GCP Marketplace. Chad identified that this morning. The geo-specific data sets we've gone through and tagged with a geotag, but you can filter by data set in there, and you can also filter by other things as well. So, you know, whether if you want to filter by transportation, whatever. A couple of the ones I'm really excited about right now are the geo boundaries we have. So the Tiger file boundaries that are available for the U.S., the all roads files, and the census places, which gives you city limits for incorporated places. So. Check them out. We'll have a session this afternoon that walks through both BigQuery GIS and GCS datasets.
Perfect, thanks, Shane.
Yeah, thank you.
Right, so we'll steal some of Shane's thunder for later on, but we'll actually go ahead and do a query that leverages some of those data sets. So what we're going to do, say I didn't have the town boundaries, but I still wanted to have a map and do it really, really quickly. This final query in here, which we'll use Don's tool for, I'm going to go and use, you'll notice we're calling one data set from my project, my Vermont project, the VT impervious layer, and then we're calling another data set, we're going to join it on Shane's data that he's put together for the US counties. And this is a data set that Google's committed to keeping up to date, so you know you're getting the latest and greatest version that's available. And so this is just going to join it based on the counties of Vermont. So doing two different data sets here and creating a map from that. And this is not doing the percent of parcels per percent impervious per parcel. It's just looking at the percent per county. But it's still a large join. It's going to take a couple seconds. All right, any questions about that in terms of public data? Now you can see these couple counties of Vermont, and again, we can use Don's tool to style this. Data-driven, we want to change our field to impervious percentage, and this is in a different scale. Oh, did it? Or is it just because there are... Oh. Thank you. There we go. All right, so you can play around with that, obviously, and get it to the way that you like it. Okay. Now, I promised we'd talk a little bit about this. So after this class, unfortunately, the timer is ticking down on this Google Cloud project that we set up for you, and it'll all get blown away. All your work will be gone unless you did it in your own project. But we still want you to be able to use BigQuery. And so the BigQuery team, Chad, has gone through a ton of work to put together a nice intro to BigQuery GIS, but also something really cool called the BigQuery Sandbox. So the sandbox, the idea is that it is free BigQuery, and it's up to 10 gigabytes of user data stored completely free. You don't need a billing account. So if you have your personal Gmail account, an EDU account, or G Suite, doesn't matter. Don't need to have a billing account set up in Google Cloud Platform, and you also get a terabyte of queries per month. I should have mentioned this to begin with, but the way that Google charges for BigQuery is you're charged on the amount of data that you're stored. Remember, that's separate. And then the amount of compute that you essentially use to run the query. And we calculate that by the size of the queries that you run. So this is actually kind of neat. If you don't need every column in your queries, don't use star. You'll actually pay less if you only query, because we're actually pulling individual columns from storage if you only query against the columns that you really need. So star is great for quick and dirty, but you'll pay more for it if it's a big data set. You still have the full access to the public data sets that Shane set up, and you have full performance. This is not throttled. You're getting slots alongside of our paying customers to use this. The way that you get it, just search for, honestly, either take this link or just search for Google BigQuery Sandbox, or if you just set up a Google Cloud project without any billing, you will automatically be in the BigQuery Sandbox. And the way that you can tell that is there will be a little banner bar up here that says Sandbox, and if you run out of those limits, then you can put in the credit card or wait till next month. Okay, and then BigQuery GeoViz, you just Google that as well, and you'll get the access to it, and there's documentation for it. Okay.
Are the slides also available?
Yes, the slides are available. They're available. There's a URL written on the board. The slides and the documentation that was used to build the Quick Lab are available. They're available at tinyscc/G4G2019-BQGIS-doc and BQGIS-deck. No problem. Any other questions? Yes?
It's about projections.
It's about projections?
So far you say that it's only for 3 to 6.
Mhm.
Are there any plan to add more projection supported, or are you planning to keep only dealing with this one?
So the question is there plans for support for projections?
Not right now. So right now it's single projection, and you should note all the calculations are on the sphere. So one nice thing about it is you don't need to worry about anti-meridian or any issues with the area, and all the distances are correct in regardless of.
Yeah. Just to elaborate on that. So when we're calculating on the sphere, you don't have to worry about is this an equal area projection when you're doing an area calculation, right? So that is one of the nice things about doing it all based on the sphere. Yes?
We have had a couple of requests for projections, so I'm interested to hear what your use case is. But mine was quite clear. We don't have one, not right now, but people ask. Does it require any computational assistance? So if you're working in different projections and you want to import the data, then you have a lot of data. It's going to take a while before you can upload this data, and sometimes if you are in a local area and your projection is projected, the calculations are more accurate than if you are to transform to 3 to 6 and do all your calculations at 3 to 6.
Gotcha. So for high precision.
Yeah.
All right, any other questions? Great. Thank you, everyone.